Hello everyone, I'm Shupatra Pancha, Assistant Professor, Department of Computer Science and Engineering, BLD SVP Dr. PG Hakati College of Engineering and Technology, Vijaypur. So, in the last class, we have completed third module. So, we have discussed about something about randomness, then generate random number generators, freshness mechanisms. So apart from that, we have discussed some protocols also. So now in this module, we will be discussing how the key generation, how the key management will be considered for cryptography. So this module entirely deals with management. Okay, key management. So first of all, we'll check what is exactly key management. Key management is the secure administration of cryptographic keys, as you all knows, right? So we have discussed different types of encryption algorithm. One is symmetric key encryption, and another one is public key encryption. And if you want to use any one of that encryption algorithms, you need a key. And what we supposed to think here is so how you are going to generate those keys for the successful use of any of the encryption algorithms. So that is what we need a certain key management system here. So that's what key management is, the secure administration of cryptographic keys. So cryptographic keys are special pieces of data. Key management thus involves most of the diverse process associated with information security. So these includes there are certain factors which includes for the key management. So one is technical controls. We need to go for that technical control. These can be used in various aspects of key management. Process controls, policies. So we need to have some policies, practice, and procedures to play a crucial role in key management. That is what process controls. Environmental controls. Key management must be tailored to the environment in which it will be practiced. Then apart from that, we also have human factors. Key management often involves people doing things. So involvement of certain members, certain people will also be affected for key management. So apart from this, what we have is key generation concerns the creation of keys. So it is what we can call it as something else, something about the entire process of key management. What factors it includes? So first one is key establishment. So key establishment is the process of making sure that keys reach the endpoints where they will be used. That is what key establishment. So that no other intermediate person can hack the key and use the key for their further purpose. That should not happen. Key storage. So key storage deals with the safekeeping of keys. It may also be important to conduct very simple terms so you can easily understand key backup. So once we store the keys, so how to so we need to store those keys as a backup. So wherever we need, we should retrieve those keys. So that key backup, so that keys can be recovered in the event of loss of a key. And a key archival. Key usage is about how keys are used. Key change, how keys life ends in key destruction. So these are all factors which are to be considered in key management. So this is what that's what I said. You can see this the key life cycle which comes with all those phases. So initially we have key generation. Once we generate the keys, so we need to go for we need to establish the key. That's what how we are supposed to send the keys to the sender to receiver securely. And after that, we need to store the keys. So at the same time, we need to back up the key, and wherever we lost the keys, we need to retrieve the key from this key backup. Then after that, what we have is so wherever we need to usage, we need to use the keys. That is what key usage. So key usage in the sense we need to use it in the proper optimization level. That is by with the help of key archival. Then wherever we are supposed to we are assumed that key usage is completed or it is finished. Then what we have to go for is key destruction. We have to delete that entire key for our usage. Then after that key usage, if you want to change the key, then again it will go to the key change phase. Then again once again it goes to the first phase of that key life cycle, that is generation. Then again it continues as a cycle. That's what we can call it as a the key life cycle. There are two fundamental key management requirements that apply throughout the various phases of the key life cycle. Secrecy of keys, then assurance of purpose of keys. What is secrecy of keys? You know already. Throughout the life cycle, secret keys, in other words, symmetric keys and private keys must remain secret from all parties except those that are authorized to know them. Assurance of purpose of keys throughout the life cycle, those parties relying on a key must have assurance of purpose of the key. These two factors are very important. We need to keep keys as secret. Then, if anyone wants to use, then so he or she should produce the assurance of purpose of key. Key management continued. Uh, After that key life cycle, what we have is key management system may depend on. So whenever we are generating with the help of key life cycle, whenever we are generating, what's that keys with a certain with the different phases of key life cycle at the same time. So which system we are supposed to use for doing such things? So key management system may depend on the network topology, cryptographic mechanisms, then compliance restrictions, legacy issues. So these are all factors, right, related to technical issues. Topology, you know already, cryptographic mechanisms, compliance restrictions, then legacy issues. So apart from this, we have one more is that is key lengths and lifetimes. So which type of length we are supposed to generate, right? Then up to which time the key should be existed. So those 2 points are very important as a point of key management. The longer keys are better from security perspective. A cryptographic computation normally takes more time if the key is longer. In addition, longer keys involve greater storage and distribution of overheads. So that's what key lifetimes. So we'll discuss in brief one by one. So something about lifetimes and longer. There are many reasons why cryptographic keys have finite lifetimes. So these include mitigation against key compromise, mitigation against key management failures. So that's what we need to take care of these points. Mitigation against future attacks, enforcement of management cycles, flexibility, limitation of key exposure. Just to have a concentration on these points. There are many reasons why cryptographic keys have finite lifetime. To overcome all this, so we should have a finite lifetimes of key. Next, something about key generation. So we'll discuss step by step. That is key life cycle phases one by one. So in that first one is key generation. Key generation process for symmetric and public cryptography are fundamentally different. So in that we have one is direct key generation and another one is what we have is okay, we'll discuss the next one next. So the first one is direct key generation. In this, symmetric keys are just randomly generated numbers, so normally bit strings. The method for generating cryptographic key is to randomly generate a number or more commonly a pseudorandom number. I think we have discussed how to generate random numbers in the previous model. The choice of technique will depend on the application. That's what direct key generation that will happen only in this symmetric keys, right? Key derivation. Second one is uh, after that key generation we have key derivation. The term key derivation is the generation of cryptographic keys from other cryptographic keys or secret values. Advantages of deriving keys from other keys. So what is the advantages of deriving keys from other keys? So we should discuss about those efficiency. So what is exactly that efficiency? Efficiency means generating and establishing one key, sometimes called a base key, and then using it to derive many keys. For example, many applications require both confidentiality and data origin authentication. If separate cryptographic mechanisms are to be used to provide these two security services, then they require an encryption key and a MAC key. It means very simple. So we'll be using one base key, and from that base key we'll be deriving another key. That is what we can call it as a, here you can see this encryption key. From that we'll be deriving MAC key. It's a good practice to make sure that the keys used for each of these mechanisms are different. Rather than generating and establishing two symmetric keys, for this purpose, a cost-efficient solution is to generate and establish one key K and then derive two keys K1 and K2 from it. At the same time, we'll be using K1 and K2 for two different purposes. Then something about longevity. In some applications, long-term symmetric keys are preloaded onto devices before deployment. Using these long-term keys directly to encrypt data exposes them to cryptanalysis. Randomly generating a new key requires a key establishment mechanism to be used, which may not always be possible or practical. A good solution is to derive keys for use from the long-term key. There is one example about this key management. For example, PKCS5, it's an algorithm. There's something else about private key cryptographic system defines how a key can be derived from a password or a PIN, which can be regarded as a relatively insecure type of cryptographic key, but one which is often long term, such as the PIN associated with the payment card. The key derivation in this case is defined as a function. So there is one function how we are going to derive the key. So we'll be defining that key derivation in the form of function called as f of p comma s comma c comma l, where so what is p, s, c, and l? Where f is a function, f is a key derivation function that explains how to combine the various inputs in order to derive a key. P is the password or pin. Alright. S is the string, not necessarily all secret pseudo-random bits used to enable P to be used to derive many different keys. C is any iteration counter that specifies the number of rounds to compute. L is the length of the derived key. This is what general function which is used for key derivation. So and another source is for key generation from components. I think we have discussed. One is, so in the key generation process, it comes with the two types. One is direct key generation, and another one is key generation from components. So what is exactly that key generation from components? So consider a simple scenario involving three entities. So I think I already told that the actors of this INS subject, Alice, Bob, and Charlie. Assume that we wish to generate a 128-bit key. Alice, Bob, and Charlie each randomly generate a component of 128 bits. Alice, Bob, Charlie securely transfer their components to a secure combiner. These secure component derives a key K from the separate components. So in this example, the best derivation function is XOR, that is K equal to KA XOR KB XOR KC, which collectively generates one key called as K. Thus, Alice, Bob, Charlie are able to jointly generate a key in such a way that all three of their components are all three of their components are necessary for the process to complete. If only two of the components are present, then no information about the key can be derived, even if the components are combined. This is what the theme of this key generation from components is very simple. If a multiple users want to use the key, then they should have certain algorithm. Then combinedly all users should generate one key, and all users should use that key securely one from the another by referring that particular algorithm. That is what key generation from components. Next we have is public key pair generation. I think in public key pair generation, the one best algorithm we'll be using for public key encryption, that is RSA algorithm. So key generation for public key cryptography is algorithm specific. For example, for RSA, the keys D and E are required to have specific mathematical properties. If we choose an RSA modulus of 1024 bits, then there are, in theory, 21024 candidates for E or D. I think we'll be using E and D for public and private key D. However, only some of these 21024 numbers can be an E or A. The other choices are ruled out. Some keys in public key systems are chosen to have a specific format. The generation of key pairs can be slow and complex. Some devices, such as smart cards, may not have computational resources to generate key pairs. So this is about another form, that is public key pair generation. That is the best example for this is we'll be using is RSA algorithm. Then the next phase of that life cycle is we have, after key generation, we have key establishment. So in this key establishment, what we are supposed to do is we need to transfer the key securely to another user. The key establishment is the process of getting cryptographic keys to the locations where they will be used. The keys does not need to be shared. The key does not need to be shared. The key can be established in a controlled environment. Key hierarchies. So key hierarchy is a technique used for managing symmetric keys. This consists of a ranking of keys, with high level of keys being more important than low level keys. Keys at one level are used to encrypt keys at level beneath. So this is what key hierarchies. So philosophy behind key hierarchies. There are two advantages of deploying keys in a hierarchy: secure distribution and storage, facilitating scalable key change. A simple key hierarchies. The idea of key hierarchy is illustrated considering a simple example which is shown in the figure. The three levels of hierarchy consist of master keys, key encrypting keys, then data keys. So that figure I'll show it to you in the next class, of course. Okay. So we'll stop it here, and in the next class we'll be discussing about managing the top level keys.